Hello, am I audible? Okay, thank you. So let's wait for 1 more minute. It might some people's join. So in the meantime, I will share my screen. Okay, so hope my screen is visible. Okay, so let's start. So hello everyone, I am Subrata Samanta. So I am one of the TA for the thermal physics course that is taken by Professor Dev Banerjee. So in these sessions, I will discuss the assignment 10 problems. Okay. So basically, I'll solve the previous year assignment 10 problems. Okay, and hope you at the end you are able to solve this week assignment year problems. Okay, so it's very similar to these problems. Okay, that's I will solve today. Okay, and if you have any questions, you can ask directly. Okay, unmute yourselves and ask the questions. Otherwise, you can also write in the chat. Okay, so is there any questions from the week content? Okay, so or any previous year assignments? Okay, previous week assignments. Is any questions is related to the content that is you have completed so far? Okay. Okay, so it seems there is no more questions. So then I will start to continue to solve the problems. So in the first problem, so if U is the thermal energy of a gas, right, obeying the diatrice equations, okay, this is basically P equals to RT over V minus V and then exponential e to the power A over RTV. Then del U del V at constant temperature is equals to, okay, so you have to calculate this. Okay, so first, what is the equations of state? Now the equations of state is basically deterioracy, so is P equals to RT over V minus V e to the power minus A over RTV, right? So in order to calculate del U del V, so how to calculate del U del V? So first we know that your du equals to, so if u is a function of s and v, so then we can write du is basically del u over del s at constant volume v times ds, right, plus del u over del v at constant s times dv. This is the property of the partial differential equation, right? So if is a functions u is a functions of usv, then we can write this. Okay, total derivative du is basically the partial derivatives. Okay, del u del s at constant v ds plus del u del v at constant s dv. So this you can write that tds, right, minus pdv. Okay, so where t is basically del u del s at constant v, so where t del u del s at constant v and p is minus del u del v, right, at constant s, right. So you have to calculate del u del v, right. So this is a du So now next, so let's first copy this and go to the end. So get a new page. So the problem number 1. Okay, so this is your problem, right? So this is the equations of state that is given. Okay, so now you have to calculate del u del v. So del u over del v at constant temperatures then is basically T times, right, del S over del V, right. So T ds, so del S over del V at constant temperature minus P, right, from this equation. So the equations is basically your du equals to this, right. So from these equations you just take one more derivative with respect to V. Okay, so this is this one. Okay, so we end up with these equations, right. So now this del S del V at constant temperatures, because in the problem only P is given. Okay, pressure is depends on how it depends on volumes, this is given, right. So we use Maxwell equations, right. So use Maxwell equations. So what is the Maxwell equations? Is that del S del V at constant temperatures is equals to del P del T at constant volume, right. So once we use this, just put this here. So T del P del T at constant volume minus P, right. Now we know, because P is basically RT over V minus B. So RT over V minus B e to the power minus A over RTV. So it is straightforward to calculate del P over del T at constant volume, right. So okay, so we derivative with respect to P. So first we derivative the first term, so R over V minus B e to the power minus A over RTV, right. So RTV. Okay, let's first right. So then plus the second term, right. So RT over V minus B minus A over RT square V plus times e to the power minus A over RTV, right. So that means if we just take commons, that R over V minus B e to the power minus A over RTV times 1 plus, so 1 plus A over R by V minus over V minus B, so A over TV, yeah, so A over RTV, sorry, A over RV, because T square is 1 over T. Okay, wait 2 minutes, 1 over T. So yeah, so this is basically A over RTV, right, RTV. Okay, so now we put this in this main equations. So this is basically T times, so R over V minus B e to the power minus A over RTV. Now we multiplied with a T, right. So this is basically T plus A over RV minus P. Again we just put the equations of P. So RT over V minus B, right, and then e to the power minus A over RTV. Okay, so this is nothing but we just cancel the first terms. Okay, so this one is RTV, and so because this term is cancelled with this term. Okay, so the left with A over V times V minus B, right, e to the power minus A over RTV. Okay, so you are left with this only. So therefore your del U del V at constant temperatures, okay, is equals to A e to the power minus A over RTV over V times V minus V. So this is the answer. Okay. Okay. So let's check the options. Yeah. So the C, right? So option C is the correct one. Okay. So it's clear. Any questions? Don't hesitate to ask any questions. Okay, if you have any. So unmute yourselves and ask the questions directly. Okay. If you have any questions on that, to clarify your doubts. So this is basically very straightforward. So first you calculate du equals to TdS minus PdV. Okay, use these relations and take one more derivative with respect to V, right? And the second step is that use the Maxwell equations. Okay, you have to use one Maxwell equation. So this is the Maxwell equations. So if you use this, because we know how P changes with temperatures, right? Not how S changes with volume. So S is entropy, right? So you first convert this. Okay, so del S del V to del P del T, because the information is given how P changes with temperatures, right? So we use this. That's why we use one Maxwell equations in the second steps. Okay. Now it's straightforward. Just take derivatives. Okay, and to calculate del P del T. Once we calculate this, we just plug into the main equations. Okay, and we finally got the answers. Okay. So now going to the next problem. So is the problem number 2. So find the amount of heat transferred when the pressure of 1 mole of mercury at 0 degree centigrade is increased isothermally and reversibly from 0 to 1000 atm. Okay, given the volume of 1 mole is 14.7 cc and the volume expensivity 178 times 10 to the power minus 6 per degree centigrade. Okay. Okay, so first you have to calculate the amount of heat is transferred, that means delta Q, right? So this is the amount of heat is transferred when the pressure of 1 mole of mercury at 0 degree centigrade is increased isothermally, right? So what is the formula for delta Q? So you know that the delta Q is basically T delta S, right? So basically we know that the dQ, I mean, it's the more familiar form. So dQ is basically TdS, right? So now if we use the TdS relations, okay, that is most frequently derived in the class. Okay, so this is basically TdS equals to CPdt minus TV, the alpha is the volume expensivity, right? So TV alpha and dP, right? So where alpha, so I just copy this. So alpha is the volume expensivity. So where alpha is the volume expensivity, right? So volume expensivity, okay, and that is given. Okay. So what is the values? What are the values given here? So the alpha value is given. So alpha is 178 times 10 to the power minus 6, and the volume is given. V is 14.7 cc, right? So convert it into meter cube, right? So how to convert? So 14.7 times 10 to the power minus 6 meter cube, right? So we convert cc to meter cube, okay. And other thing is that, yeah, so pressure is 1 atm, so your delta p is basically 0 to 1000 atm. So delta p, the change in pressure, is basically 1000 atm. So convert into Pascal, right? So 1000 times 1.013 times 10 to the power 5 Pascal, right? And the temperature is given, so as 0 degree centigrade, that means 273 Kelvin. So temperature is 273 Kelvin. Any other thing? No. A mole is 1 mole. Okay, so that's fine. So then we have to calculate the amount of heat transfer, I mean delta Q. So this is basically T delta ds. So use this data. Okay, so you can calculate delta Q. So the problem number 2. Okay, so use this data. Okay, so it is straightforward to calculate delta Q, since delta Q is basically your Cp. So yeah, so one more thing is that delta T is dt is 0, right? So because isothermal, right? So isothermal expansion, expansion. Okay, so this implies that dt equals to 0. So that means delta Q is basically minus Tv alpha delta P, right? So we plug this value, minus T is 273 times V is 14.7 times 10 to the power minus 6 meter cube, right, times your alpha is 178 times 10 to the power minus 6 times your delta P is 1000 times 1.013 times 10 to the power 5 Pascal. Okay, that is basically Newton per meter square, right? So Pascal is basically 1 Newton per meter square, right? So ultimate unit is your joule, right? So basically use your calculator to calculate the number. So this is basically minus 72.36 joule. Okay, so please cross check this. Okay, so minus 70.36 joule. Okay, in short J. Okay, so joule, right? So this is delta Q, minus 70.36 joule. So let's check the option. So minus 72.36. So it's very close to minus 72.4, right? Okay, so very close to minus 72.4. So the option, which option? So, yeah, so option D is correct. Okay, yeah, any question? Okay, so it seems there is no more question. So then I will move to the next one. So in the next question, So basically the pressure on a block of copper, okay, weighing 1 kg is increased reversibly to 1000 atm at 15 degrees centigrade. Find the values of Cp minus Cv for the process where the alpha is given, Kt is given and volume is given, right? So volume is basically meter cube per kg is given, not per mole. Okay, so you first convert this per mole. Okay, what is the volume per? Okay, so what is the, so finally you have to calculate Cp minus Cv, right? So what is the expressions to calculate Cp minus Cv, right? So what is your Cp and Cv, right? So let's first derive this. Okay, so how to calculate Cp minus Cv from the quantity that is given. So the quantity is given is basically this, okay, alpha and Kt. Okay, so alpha is the same alpha as in before, the volume expensivity, okay, and Kt is the isothermal compressibility, right? So Kt is the isothermal compressibility, right, and alpha is the volume expensivity. Okay, so first we derived Cp minus Cv in terms of this, right? So it's problem number 3. Okay, so what is Cp, right? So Cp is basically dq del q over del T at constant pressure, right? Okay, so now we know that dq is basically TdS. Okay, so this is basically so TdS minus PdV. So when you say that, no, dq is basically du is TdS minus PdV. So dq is TdS, so this is basically T del S over del T at constant pressure. Similarly Cv is T del S over del T at constant volume, right? So Cp minus, this is basically okay, so del Q, Cp minus Cv, then T del S del T at constant pressure minus T del S del T at constant volume, right? So now we know that F is a function of T and V, right? So F is a function of T and V. So that means your ds, okay, so it's basically again we use the partial, so del S del T at constant volume dt, right, plus del S del V at constant temperature dV, right? So differentiating with respect to T at constant pressure, so we differentiate with respect to T at constant pressure. So this is basically del S del T at constant pressure, okay, is equals to del S del T at constant volume plus del S del V at constant temperature times del V del T at constant pressure, right? Okay, so now if you multiply it with a T, so this basically T times del S del T at constant pressure minus T times del S del T at constant volume equals to T times, right, del S del V at constant temperature times del V del T at constant pressure. Okay, so here we multiplied with a T this and multiplied with a T this, okay, and take left hand sides, okay. So this is basically minus, okay, which is equals to again multiply T times del S del V. So basically multiplying both sides, okay, with a T, okay, and the first terms, okay, take lefts, okay, right. So now, so the left hand side is exactly the same this, okay, exactly the same as this, okay? So therefore which is equals to T del S del V at constant temperature times del V del T at constant pressure, right. Now okay, so now del S del V at constant temperatures is basically, so the second step is that, so let's first box this one, okay. So I have to do more, Cp minus Cv equals to this. So now we rewrite this del H del Vt because we can use Maxwell equations, right. So use Maxwell's equations. So then del S, so del S del V at constant temperature, which is equals to del P del T at constant volume, right. So now del P del T at constant volume is equals to minus del P del V at constant temperature and del V del T at constant pressure, right. This is basically f of PVT equals to 0, so you can rewrite the del P del T V plus this, okay. So we can rewrite this, okay. Right. Now we plug this into this equation. So now the Cp minus Cv then is basically your minus T times, so del H del V T basically this, okay. So minus T del V del T P del P del V T and del V del T P, right, okay. So you can rewrite this is basically this that, so V times T and 1 over V, because we multiplied with V and divided by V, so 1 over V times del V del T P times 1 over V again del V del T P divided by minus 1 over V del V del P, right. So I reverse this, okay. So del P del V I inverse, okay. So basically del V del P at constant temperature T, right, because the temperature is constant. So you can use this property that del P del V at constant temperature equals to 1 over del V del P at constant temperature. So since both are the same at constant temperature, we can inverse this, okay. Del P del V equals to del V del P, okay, at same constant, okay, constant temperature. If the constants difference, okay, I mean if you take a partial derivative with respect to V, okay, while the T is fixed, that not equals to, that is not equals to if we consider, let's say S is fixed, right. So provided the T is fixed, then it's equal. Okay. Same thing, same constants parameters are there for the both the cases. Okay. So this is basically equals to, so this is on Vt, okay, and this one 1 over V del Tp is basically your alpha, okay, is the volume expansivity alpha square, okay, because the same thing here, right, divided by 1 over minus 1 over V del Tp is basically Kt, right. So where alpha is 1 over V del T at constant pressure, right, and Kt is minus 1 over V del P at constant temperature. So I already told you that alpha is the volume expansivity. So this one is the volume expansivity and is the isothermal compressibility. Isothermal compressibility, right. Okay. Okay, so isothermal compressibility, this is the volume expansivity. So in the given problem, so alpha, Kt, Vt all are given, right? So you have to calculate Cp minus Cv. So we use these relations. So Cp minus Cv. Then what is the volume? First of all, what is the temperature? Okay. So the temperature is given. Yes. So Kt, the values of Kt is given 8.6 times 10 to the power minus 12. Right. Alpha value is 5 into 10 to the power minus 5. And V value, the volume is 0.000342114. This is meter cube per kg. Okay, and there is a 1 kg of 1 kg of copper. Okay, Cu, and the temperature T is 15 degrees centigrade, so 288 Kelvin, right? Okay, so please correct me if I wrong. So yes, so this is basically 288 Kelvins. Okay. Okay. So one more thing we have to do, since the volume. So volume is given meter cube per kg. Okay. So first converted this meter cube per mole. Okay. Why? Because your answer is given. Your answer is given in mole inverse, right? Not the kg inverse. So how to convert this? So just closely look into this. So answer is given mole inverse. Okay. So okay. So how to convert this kg to mole? So what is the molar mass of copper? So molar mass of copper is basically 63.546 U, right? The atomic units. Okay. So therefore, 1 gram of copper. So basically 63.546 gram of copper, right, equals to 1 mole. So 1000 gram of copper. So 1 kg means 1000 gram. So 1000 gram of copper equals to 1000 over 63.546, right? 546 mole, so which is equals to 15.7 mole, right? So therefore the volume V equals to 0.000114 divided by 15.7 meter cube per mole, right? Okay, so rest of the things is fine. Okay, so rest of the things are fine. So then the volume, the temperature is basically 288 times this, so Cp minus Cv is 288 temperature times your volume 0.00000114 over 15.7 times your alpha. Alpha is 5 into 10 to the power minus 5 square divided by Kt. So what is the values of Kt? 8.6 times 10 to the power minus 12. Okay, so now what is the unit? So unit is basically your joule Kelvin inverse mole inverse, right? So remember, joule is basically Newton meter, right? So 1 joule is basically 1 Newton meter. So after simplifications, okay, this yields 0.61 joule Kelvin inverse mole inverse. Okay. So answer is 0.61. Okay, in the units of joule per Kelvin per mole. Okay, so let's check the option. Yes, the option A is correct, right? Okay, so option A is correct. So unit is joule per Kelvin per mole. Okay, so far any question, any doubts? So first we derive that Cp how the Cp minus Cv is related to your alpha and Kt. Okay, so once you derive this, or if you know the formula, you directly use this. Okay, and then you calculate this. Okay, so one of the tricky part here. So the volume is basically given mole meter cube per kg. So you have to convert it per mole. Okay, from that molar mass. If you know the molar mass of copper, you can calculate. So this is basically 1 kg because the 1 kg of copper, sorry, in the problem. So that's why I use 1 kg equals to 1000 gram, right? Okay, so any questions? Okay, so it seems there is no more questions, so then I'll move to the next one. Okay, so the next problem is basically the expression is equivalent to. So the expression is del P del V at constant temperature times del T del P. Okay, so which is equals to so your final expression is only one derivatives. Okay, any of the four options. Okay? have only one derivative. So we have to choose the Maxwell equations. Okay, I have to choose which Maxwell equation. So first, let's say del T del P. Okay, so you know that del P del T del P at constant S is equals to basically del V del S at constant temperature, right? So this is one of the Maxwell equations. So I use this, okay, right? Because that's reduce me, because this is the constant temperature, this is also a constant temperatures. Okay, and so this helps a lot. So del P del V at constant temperature and del T del P at constant S. So I replace the derivatives, okay, where the constant is T, the same as this. Okay, so therefore I choose this. Okay, so one of the Maxwell equations. So this is basically del V del S at constant T. Now the last one is as it is, so del S del T at constant. So from these two, okay, so this is basically del P del V at constant T times del V del S. So this is del P del S at constant, okay, we keep at it. So del P del V at constant T, right? Okay, and del S del T at constant P, right? So we use a Maxwell equations, that is basically del T. Okay, wait a minute. So del S del T at constant P, that means del V del T. Yeah. So del V del T at constant P, right? No, it's not clear, right? So del P del V at constant P. Okay. Sorry, this one is basically, sorry, this is basically at constant P, right? So del V del T at constant P. Okay. Sorry. So I'm wrong. So del V del S at constant P. So this is at constant P. So now if we multiply this, so because both are constant pressure, so del V del S at constant P times del S del T at constant P equals to del V del T at constant P, right? So these two, right? So from these two, we got this, the last one. Okay. The first was as it is, okay, as it is. So now we use a second Maxwell equation. So what is the other Maxwell equation? So the Maxwell equations 2 is basically del V del T at constant pressure is equals to minus del S del P at constant temperatures. So this is minus del P del V at constant temperature times del S del P at constant temperature. So now both are same constants, right? So constant temperatures, right? So you can multiply this. So this is basically minus del S del V. So del P cancel, right? So minus del S del V at constant temperatures, right? So therefore which option is correct? So option T, right? So del S del V at constant temperature. So option D is correct. Yeah, any doubt? Any question? So here we use basically two Maxwell equations. Okay, one is this, another is this. So first we changes constant S to constant P, okay, such that we can multiply it with this. Okay, so that is the trick. Okay, because you see that the both three quantities, like all the three quantities have a different constants, right? So this is constant T, constant S, and constant P. So first we change from one constant to another such that the two constants must be similar, then we can multiply. Okay, so first we change this using one Maxwell equations. So this S to P, and then we multiply it. Okay, combined we get 1, that is constant P. Now this one is del P at constant T. Okay, so now we change P to T. Okay, use another Maxwell equation. So this is the second one. Okay, so it's P to T. Then we again multiply it because they're both the same constant. So you just multiply this, and this is basically your final answers. Okay, so the only constant is T. So that is the trick. Okay, so change only one thing. Okay. Now the which way it works, so basically you have to do a trial. Okay. So first we change. If we change, let's say, all things in terms of S, then it might not work. Okay. So it depends on only one particular thing. So only one root is works. Okay. Okay. So it seems there is no more questions. So then I'll move to the next one. So the next question is that for a homogeneous ideal gas, find out the ratio of adiabatic elasticity and isothermal elasticity where the Cp and Cv is given, right? So I hope that you know what is the ratio of this, right? So Es over Et, the adiabatic elasticity over isothermal elasticity. Let us derive this. Okay. So the problem number 5. Okay, so first I derive the Kt over Ks, right? Okay, so what is Kt and Ks? Let's first clarify this. So Kt is your isothermal compressibility. So Kt isothermal compressibility. Okay, which is basically 1 over the defined is minus 1 over V del P at constant temperatures, right? And Ks is adiabatic compressibility. Okay, so this Ks equals to minus 1 over V del P at constant S, right? So the ratio of these two is that minus sign is cancels both numerator and denominator. So is 1 over V is also cancelled. So del P at constant temperatures over del P at constant S entropy, right? So now if we use this product that del P at constant T, I can write this del T at constant P times del T and del P at constant P, right? So this is basically where we use the identity is that del P at constant T and then del T at constant P and then del V at constant P, sorry, del P So this is basically minus 1. So the product of 3. Okay, you see that the product is basically continuity. So del v del p and then del p del t and then del t del v. Okay, so it's kind of connect this. Okay, so del p and then del t, but the constant changes. Okay, so all three products have a minus 1. Okay, so I use this. Okay, so this is basically reverse. So one of this equals to the minus 1 over this, and we just changes. Okay, and the other one is that del p del t at constant v is equals to 1 over del t del p at constant v. Okay. So same constant, so I can inverse this. Okay, and the similarly the below one is basically minus del v del s at constant p and del s del v at constant p, right? So now we use the Maxwell equations, right? So first one is that del v del t at constant p. Okay, so here is constant v, so I have to change at constant p. So this is basically minus del s del v at constant p, right? Similarly, sorry, this is basically del t del p at constant p. Okay, so what I did here, so basically I take this one, so del v del s at constant p. Okay, so I'm not using here Maxwell equations. Okay, so this del v del s at constant p, I just rewrite in the numerator is del s del v at constant p. Similarly, you can also write minus del v del s, sorry, minus del s del p at constant v times, again minus, so I put here the minus sign, right? So I put extra minus sign here as well. So minus, now the numerator is del t del p at constant p, right? So you can rewrite this in the denominator is that del p del t at constant p. So now in the numerator I have a both the terms at constant p, and the denominator I have both the terms at constant p, right? And we see again, so this del p and this del p, okay, is the same. Okay, I just cross this. Okay, but the numerator is not, right? So this is basically, so the numerator is the opposite way, right? So del p, so this is basically both have plus sign, so I multiplied with a t, so t times both numerator and denominator. Let's say not, so first I write this del s over del t at constant p over del s over del t at constant v. So if we multiply both side with the, sorry, both the numerator and denominator with t, then the numerator gives is Cp and the denominator gives is Cv, right? The specific heat at constant pressure and the specific heat at constant volume. So this is, we know that the ratio is the adiabatic index gamma, right? So adiabatic index gamma, so that is basically Cp by Cv, right? So now in the given problem, so it's very simple, right? So Kt by Ks is basically gamma, right? So the given problem is basically adiabatic elasticity. So Es over Et is basically V del P del V over S equals to V del P del V over T, right? So you start with the del V del P over T, right? Here the del P del V. So that means this is also a gamma, right? Sorry, this is basically ES over ET, right? So then ES over ET is basically gamma, right? This is basically, so from these definitions, okay. So see, this is basically KT over Ks, this is gamma, right? We just derived the last one, the KT over K is equals to gamma, right? So this one, if we rewrite the denominator in the numerator, this is basically del P del V over S, right? So del P del V over S, okay. And this del P over T in the numerator, it gives the denominator is del P del V over T, right? And the VV is cancelled. Okay, so this is gamma. So therefore, your ES over ET is basically the adiabatic elasticity and the isothermal elasticity, right? So where ES is the adiabatic elasticity, okay, and ET is the isothermal elasticity, okay. The ratio of ES over ET is gamma, while the ratio of KT over KS is gamma, where the KT is the compressibility, right? And ET, ES and the elasticity, adiabatic and isothermal, right? So now in the given problems, the basically we have to calculate ES over ET, so that is Cp over Cv, right? And the Cp value is given in the problem. So what are the values? The values of Cp basically, yeah, so 50 and the Cv is 42, right? So your ET over ES is basically Cp over Cv, right? So this is basically 50 over 42, right? So it's very close to what? So 50 over 42 is very close to 1.19. So the option A is correct. Okay. Okay. Any question? Okay. So if you have any questions, you can ask. Okay. Unmute yourselves and ask your questions. Or you can also write in the chat. So, okay. So don't hesitate to ask any questions. Okay. If you have any. Okay. So it seems there is no more questions. So then I will move to the next one. So for a thermodynamic system, the expression T del S del Tp and minus T del S del Tv is always equal to, okay. So this is basically your Cp minus Cv, right? So what about the Cp? Cp is basically del Q over del T at constant pressure, right? And this is basically T del H del T at constant pressure, and Cv is del Q over del T at constant volume. This is T del H del T at constant volume, right? So the expressions that is given in the problem is nothing but the Cp minus Cv, right? So Cp minus Cv is T del H del Tp minus T del H del Tp, right? So how to compute this? I think we already work with this. So this is basically S is a functions of T and V, right? It's basically functions of two variable. Okay. So where ds is basically, so the total derivative is equals to the partial derivative del S del T, because the functions of two variable dt plus del S del V at constant temperature times dV, right? Okay. So this is nothing, and now we have take one more derivative with respect to T. So at constant pressure, right? So differentiate with respect to T at constant pressure P. So this is basically del S del T at constant pressure is equals to del S del T at constant V minus del S del V, sorry, plus del S del V at constant T times del V del T at constant P, right? If we multiply both sides with a T, so T and then T. Now this is basically your Cp, right? So Cp, and this is basically your Cv, okay, plus T del S del T, sorry, del S del V T del V del T P. So therefore Cp minus Cv equals to T del S del V T del V del T P, right? So the option D is correct. How do I know? Because so T del V del T P, and instead of del S del V T in the option is del P del T P, right? So this is basically one of the Maxwell equations. So I change this. So del S del V T is basically del P del T V, right? So it's basically Maxwell equations. So use Maxwell's equations. Okay. So if we use Maxwell equations, so we just change this. Okay. So del S del V T to del P del T V. Now it's consistent. So now it's match. Okay. Yeah. Any question? Okay. So if you have any questions, you can ask. Okay. So I'm coming in 2 minutes. So. Okay, so it seems that there is no questions. Okay, so then I'll move to the next one. So in the next question, the problem number 7. So if the equations of state is given by V equals to RT over P minus B over T square, where B is a constant. Okay, so which of the following relation is true? Okay, so in the questions, you have to compute delta Cp over delta P at constant temperature, right? Okay, so you have to compute this, and the given is V equals to RT over P minus P over T square, right? So first we calculate del V over del T, because we know that delta Cp over delta P, so there is one relation, is constant temperatures is equals to minus T del 2V over del T2, okay, at constant pressure, right? So now I'm not deriving this. If time permits, okay, at the end I will derive this. Okay. So first we use this, so use these relations. Okay, so del Cp over del P at constant temperatures equals to minus T times del 2V del T2 at constant pressure. So for the V is given, so if I take one derivatives, so this is basically R over P minus plus 2B over T cube, and take one more derivative del 2V over del T2. Okay, for the pressure is constant, right? So at P at constant pressure, so this is basically 0 minus 6B over T to the power 4, right? So this is basically minus and T times minus 6B over T to the power 4. Okay, so which is basically 6B times T to the power cube, right? So this is proportional to, so implies that delta Cp over del P is proportional to, where 6B all are constant, so it's proportional to T to the power minus 3, right? So the last one, okay, so del Cp over del P at constant temperature is proportional to T to the power minus 3. So the option D is correct. Okay. Yeah, any question? Okay, so it seems that there is no more question, so then I will move to the next one. So the problem number 8. So if the volume expansivity is given by this alpha equals to 1 over V del V del T, then find the ratio of adiabatic to isobaric volume expansivity. Alpha is alpha P, right? So alpha S is basically 1 over V del V del T at constant S over alpha P is 1 over V del V del T at constant pressure, right? So in the above case, we use the Maxwell equation. So del V del T S is basically minus, right, so del S del T V, right, so del S del T V and del V del TP okay, 1 minute. So del V del T is basically, no, this is, so del V del T is equals to del S del T V. No, this is something, is this, so this is basically, yeah, so the in denominator we can write this, so 1 over V cancel, right, so in the denominator we can write del V del Tp equals to minus del P del Tv and del T del V del Tp, so del V del Tp, right. Okay, check this. Okay, so this is basically very simple. So you rewrite first del V del T S in terms of del S del Tv, okay, and del yes, so now we multiplied both sides with a T, right, so your alpha S over alpha P is equals to T times del S del Tv over minus T times del P del Tv times del V del Tp, right. So now we just derived in the previous, so here the Cp minus Cv is basically your T del S del Vt and del V del Tp, right. So once you use the Maxwell equations, right, so the upper one is basically your Cv, so just copy this, yeah, so the 7, so the upper one is basically your Cv and the denominator is basically Cv minus Cp, okay, because Cp minus Cv is this T del P del Tv, right, and times del V del Tp, right. Okay, so it's clear. So then this is basically 1 by 1 minus Cp by Cv, right, so 1 by 1 minus gamma, right. So now what is the values of gamma? So gamma is Cp by Cv, that is given in the problem. Okay, so if you go back to the problem, yes, so Cp is 50 and Cv is 42 again, so this is basically 1 minus so gamma value is basically again I think 50 by 42, so 1.19, right, so this is basically 1 by 1 minus 1.19, so 1 over 0.19, right, so minus right? So this is basically minus 5.25, slightly above 5, because this is basically slightly below 0.2. So 1 over this, so it's slightly above 5. Okay, so 5.25. Okay, and with a negative sign. So let's check the option. Yeah, so option B is correct, right? Okay, so let's first check this one. Okay, so how this alpha s over alpha p on del v del t s over del v del t p to this equation. So cross check this. Okay, and you cross check now. Okay, so I'm coming in 2 minutes. So in the meantime, you cross check this. Okay, how to get from here to here. This is basically very simple steps. Okay? So I'm coming in 2 minutes. Okay, you cross check this. Okay, so have you tried this? Okay. Is there any issue or any problem you face to solve this problem? It's very straightforward. Okay, I mean, and then we have to use one Maxwell equations. Okay, so then we end up with this, and now we just derive this. So this is basically your Cp minus Cv. Okay, and here this is a minus sign, right? So this is basically Cv minus Cp, and the numerator is Cv. So Cv over Cp minus Cv. So this is basically 1 over 1 minus gamma. Okay, so let's check, is there any questions? Okay, so there is no question. So then I'll move to the next one. So in the next question is that if G and F are the Gibbs free energy and Helmholtz free energy respectively, then which of the following is true? Okay, so how the Gibbs free energy and Helmholtz free energy related? So F is the Helmholtz free energy is basically G minus PV. Okay, or in other words, G equals to F plus PV, right? So your Gibbs free energy equals to Helmholtz free energy plus PV. Okay, so I use this. Okay, so F equals to G minus PV because in the options, okay, all are basically F equals to something. So that's why I choose this one. So F equals to G minus PV, and now is V is related to, so this is basically G minus P times V is related to del G over del P at constant temperature. So volume is basically related to the derivative of Gibbs free energy with respect to P at constant temperature, right? So this one is basically, then you use this. So this is basically your minus P square, right, del P and then G over P. Okay, so check if a derivative with respect to P of G over P, then so it's just I think backwards. So del P, sorry, so del P G over P is basically 1 over P del G over del P minus 1 over P square G, right? So if you multiply with a minus P square, so if you multiply with minus P square, so this is basically minus P square, so this is G minus P del G del P, right, at constant temperature T. So therefore both things at constant temperature T, right? So basically same thing. So now, so this becomes one more thing, that so now we know that del P 1 over P is basically minus 1 over P square, right? So this is basically del G over P over del 1 over P, right? That is basically at constant temperature. So del G over P and del 1 over P. So option B, right? So option B is correct. So the last point is clear, right? So because del P 1 over P is basically minus 1 over P square. So if we say 1 over del 1 over P, right, so it's basically minus P square del P. So I think it's clear, right? Okay, so any doubt? Okay, so it seems there is no more questions, so then I'll move to the next one. So this is the last one. So calculate the change in Gibbs free energy in the following reactions for 1 mole of glucose. Okay. So glucose is 6C6H12O6, right? So this is the glucose, and the reaction is that 6O2 equals to, goes to 6CO2 plus 6H2O, right? So the Gibbs free energy, so the change in Gibbs free energy, okay, so change in Gibbs free energy, okay, of the reaction is given by, so your delta G, okay, the change in Gibbs free energy is basically, this is the product, the Gibbs free energy of the product minus sum over G minus sum over G, the reactant. Okay. So what are the product in this process? It's H2O and CO2, right? So therefore the delta G is equals to sum over, so 6 times, what is the Gibbs free energy for CO2, right? So it's given in the problem, right? So it's 910. Sorry, this is the glucose. So CO2 is minus 394.4. So minus 394.4 plus 6 times, what is the yeah, so the formation energy, that is basically your Gibbs free energy. So minus 228 228.6, so minus 228.6. So check the units, all are in the same units, kg per mole, right? So this is the product first, okay? So this is the product things minus reactants, right? So C6H12O6, the glucose, so is the 1, so 1 times minus 910, right, minus 6 times 0, right, because the formation energy of O2 is 0, right? So formation energy of O2 is 0, okay. So this is 6 times 0. So therefore the total change in Gibbs free energy delta G becomes minus 2828, and the unit is kilojoule per mole, so kilojoule per mole. So minus 2828, okay. So the option A is correct, okay. So any question? So basically we first calculate the G product, okay. So there the product is basically sum of G product. So there is a two product, one is CO2, another is H2O, okay, and it's 6 times, okay? So 6 times the formation energy of CO2, right? So this is for CO2, this is for H2O, okay, this is for glucose C6H12O6, okay, and this is the O2, formation energy of O2 is 0, okay, and minus the sum of reactants, okay, reactant, okay. So minus the formation energy of reactant, that is basically a change in the Gibbs free energy, okay. So any question? And where you use the formation energy of O2 is 0, so that is the information that is not given, so you have to use that. Yeah, so any question? Okay, if there is no more questions, then I will solve on extra problems. So that is basically what is the problem. So I down the problems. So problem is that consider the equation of state, equation of a state of a matter is P equals to alpha T cube over V, right? So that is the equations of state. And the internal energy of the matter is, so this is the equations of state, how the PVT related. Okay, so that is basically some P equals to alpha T cube V. Okay, and the internal energy of the matter is okay, so it's basically U TV. So that is A T to the power N ln V over V naught plus f of t, some functions of temperature. So you have to find, so the question is find, okay, A and N. Okay, so this is the problem. Okay, so you have to find A and N. Okay. So two things we have to calculate, A and N. So how to compute? Okay, so U is given, right? Okay, so you first compute what is ds. So ds is basically, so you know that the TDS equals to du plus PdV, or in other words du, we know that du is TDS minus PdV, right? So I just use these conventions, I wrote TDS equals to du plus PdV. So this implies that ds is basically du plus PdV over T, right? I straightforwardly wrote this. This is basically 1 over T. So now we can write that du, basically u is a function of let's say s is a function of, sorry, u is a function of T and V. Okay, and du is basically del u del T at constant V times dt plus del u del V at constant T, okay, times dV. So we put it here. So this is 1 over T, du is del u del V at constant T plus P over T, right, is times dV plus del u, so 1 over T del u del V at constant temperature times, sorry, at constant volume times dt, right? So it is clear. So what next? So next is basically, so now we know what is basically your u, right? So this is u is given. So then first calculate del u over del V. So first we calculate this quantity. Okay. So 1 over T del u over del V at constant temperature plus P over T, right? So which is equals to 1 over T. So u is this, so just copy this one. So this is u, so del u del v, so that means times a to the power n 1 over v, v naught over v, right, times 1 over v naught. Okay. No, this is basically yeah, so times 1 over v naught. So first with this and then take one derivatives, right? So plus f of t, so this is 0, plus p of p by p over t, right, where the p is basically alpha t cube over v, right? So p alpha t cube over v times t. So this is basically your a t to the power n minus 1 plus alpha t square over v, right? Okay. Okay, so this is the first thing, and now next the second one, okay? This one. So 1 over t del u del t v, 1 over t del u del t v. So this is basically 1 over t, so a t to the power n minus 1 n ln v over v naught plus del f over del t, because f is a function of t, right? That's it. So now if we plug these two equations here, so this is basically ds. So in this equation, so let's say a equations. So equations a becomes your ds is a t to the power n minus 1 plus alpha t square over v times dv plus f prime. So this is double derivative with respect, sorry, single derivative with respect to t over t plus n a t to the power n minus 2 ln v over v naught times dt, right? So now you know that this ds is exact differentials, right? So let's say we denote this as a m and I denote this as a n. Okay, since ds is a exact differentials, so this ds exact differential. Okay. So that means del m over del t. Okay, so m dv and this is n dt, right? So this is basically m with respect to del t. So del m over del t equals to del n over del v, right? So which gives, so del m over del t means, so after simplifications is basically 2 alpha t minus a t to the power n minus 2 equals to 0, right? So which implies that 2 alpha equals to a t to the power n minus 1. So no, this is basically n minus 3, right? So this is your equations. So this is basically a equals to 2 alpha, sorry, this equations I think we just some other name. So this is, let's say this is a star. Okay, so from equations star, that's becomes convenient. So a equals to 2 alpha and t to the power n minus 3 equals to t to the power 0. So left hand side there is nothing, means that t to the power 0. So this is because n minus 3 equals to 0. So which implies that n equals to 3. So the values of n equals to 3 and a equals to 2 alpha, right? So this is a, this is n. Okay, so this is the answers. Okay. Yeah, any question? So check this. Okay, so this is your homework. Okay, so from this to this. Okay, this is your homework. Where the m is given, so this is your m and this is your n, right? So if you use this, okay, and take one derivative with respect to t, okay, so derivative of m with respect to t equals to derivative of n with respect to v, and we get this. Okay, so check this equation. Okay, so it seems there is no more questions. So the next is in, so next is in some April. I'll just check. Yes, so April 6th, right? So 6 April 2025 at 4 p.m. right? The meeting link is same. Okay. Okay, so it seems there is no more questions, so then I'll stop the session here. Okay. So see you the next Sunday at 4 p.m. Okay. Tata. Bye bye.